Good morning, and welcome to Tulane University. It is my pleasure to introduce our next session, How Better Materials Get Us to Net Zero. If time allows at the end of the session, the panel will take questions submitted by the audience. To submit a question, please scan the QR code located on the screen. Please be sure to silence your cell phones. Enjoy the conversation, and please join me in giving a warm welcome to our moderator, Keith Brannon.
Good morning, everyone. Welcome to our session on how better materials get us to net zero. Thank you for joining us as we explore how advancements in material science and engineering are shaping the future of energy and helping us meet the urgent challenge of reducing carbon emissions. Materials are at the very core of our path to net zero. They form the foundation of everything, from energy infrastructure and transportation systems to battery technology and advanced manufacturing. But it's not just about creating better materials. It's about creating materials that can scale sustainably, work across industries, and support a future where we achieve both energy efficiency and environmental responsibility. Today, we're fortunate to have a group of leaders who are making remarkable strides in these areas, representing both academia and industry. Please join me in welcoming James Martin, CEO of Gulf Wind Technology, who is leading efforts to enhance wind energy capabilities through advanced materials right here in Louisiana. Douglas Chrisey, the Jung Chair of Materials Engineering and a physics professor at Tulane School of Science and Engineering. Dr. Chrisey brings an in-depth perspective on materials research and its applications in sustainable energy. And then Alex Girau, he is CEO and co-founder of Group One, whose team is working to commercialize potassium-ion batteries, a groundbreaking critical mineral-free alternative to lithium-ion technology. Alex has worked on 2 Nobel Prize-winning innovations, quantum dots and lithium-ion batteries, and he's a Tulane graduate. He was part of Dr. Chrisey's lab. Today, we're going to be talking not only about the exciting potential of these new materials, but the challenges and opportunities they present together. We'll explore how these advancements can fundamentally transform energy systems, reduce emissions, and position Louisiana as a leader in sustainable energy. So let's dive in. I'd like each of you just to give about 2 to 3 minutes background about your companies and bios and where you fit in to advanced materials in terms of this discussion. James, start us off.
Thank you very much. Morning, everyone. Founder and CEO of Gulf Wind Technology. Actually moved to Louisiana in 2010. Been in wind energy for a couple of decades now, and based over at the Avondale shipyard, just on the other side of the river. The great thing about wind energy that I see is it's basically the energy business, and it's a huge scaling demand for the power source. There's about 90,000 wind turbines in the US today, 120,000 employees, and it's set to grow at a rate of 7 to 10,000 turbines a year. So just breaking that down on the system level a bit more, that's almost 40, 50 units per day. So it's almost like mass producing aircraft. So we're going to talk a lot about where Gulf Wind sit in that, what Louisiana can really focus on and be expert in. We are an energy powerhouse here. We've got a lot of the base product materials in our backyard. And really excited to be here and explain a little bit about the wind industry from a system level and how advanced materials play a part down to the material science level, and really where more advanced materials and novel applications can actually reduce the cost of energy.
Douglas.
So as an academic, we only have 45 minutes to talk about myself. I'm a physicist with a passion for materials, and it started with high temperature superconductors for sure. A ceramic oxide material, went on to ferroelectrics, ferrites, and other materials, including polymers, biomaterials, engineered tissue constructs, tissue engineering. More recently, since I'm old, that means the last decade and a half, working also on energy storage materials, novel energy storage, machine learning, um, supercapacitors, and one more, quantum bits more recently. But I'm pretty much interested in everything except for metallurgy, and just have a passion for material science and new materials and what they can do. I'll just say I want to say one more thing. I work with materials both to see if we can do something that can't be done otherwise, that has important applications, and then ways with which to make materials in a scalable way. You had mentioned that.
Great. Alex.
Yeah. First thing, thank you for coming to listen to us. CEO and co-founder of Group One. Company's start has a lot to do with my connection to New Orleans and Tulane. So I come from a family of engineers and born and raised in New Orleans. And Hurricane Katrina hit when I was a senior in high school, and that completely, everybody who went through it, it was life before and then after, and it really got me attuned to the issues that climate change are much more evident now. But at the same time, the city was came on this entrepreneurial rebuilding effort, and that's where I found my chops as an entrepreneur. So I found myself being a scientific entrepreneur. So this is my second battery material venture, and we're enabling critical mineral-free alternatives to lithium-ion batteries. And we're not replacing lithium. We're never going to replace it, but there will be a gap between the demand and the supply of lithium. And also, because of the price volatility of lithium materials, we're looking for alternatives. And Group 1, short for the first group periodic table, lithium, sodium, potassium. That's where the name comes from. But my last materials venture was based out of my PhD work I was doing at Tulane on silicon nanomaterials. And instead of finishing, I spun it out in what would be a company, and to build my first prototype, Doug gave me a little spot in his lab to make some prototypes, and ended up, a few years later, raised $30 million in venture capital, built a company of 50 plus people, working with Toyota, VW, BMW, and really found myself knee deep in the world of material science and how that impacts net zero.
So Alex, one of the things that I explained to all the panelists is I know everyone is there are a lot of very smart people here, but there are also people probably more like me who will not know about advanced materials beyond a consumer. So lithium-ion batteries, that's the type battery that's in our computers, that's powering EVs. Why is lithium a problem, and what is your company seeking to solve by going with a potassium-ion alternative?
Yeah, lithium's not a problem. Mm-hmm. Just there's an asynchrony between. It takes 10 years to go from broken ground to actually an operational lithium mine. It takes 3 years to go from broken ground to an operating battery factory. That itself is a chemical engineering problem. You don't have systems that scale. So you go backwards, you don't have enough materials to supply all the cell manufacturing capabilities. So that necessitates looking for alternatives to lithium. And in addition to the alternative, we want to eliminate critical minerals such as cobalt, nickel, things that are mined from areas of socioeconomic unrest, and also the end users, for example, the automotives, if they want to realize their electrified future, they need to get their EVs down to $25,000 an EV. You can't do that by making the car better. Well, that's like squeezing blood out of a turnip. You need cheaper materials at the end of the day.
Mhm.
And so that's the entire motivation for why Group 1 exists.
And Alex was telling me that the potassium ion can be 30% cheaper to produce a battery than the lithium ion.
Yep. So we actually have world's first potassium ion battery here, and well, this is we have several of these. I just brought one out to show that this is, not a publication that's being shoved in a drawer and just getting citations. We're actually pushing technology up the TRL ladder into product, and then right now it's on the cusp of productization and industrialization. But the story's the same all over, whether you're in stationary storage or renewables or EVs. Everybody needs cheaper batteries, and there's only so many ways to make them better until you get to the fundamental physics. You need better materials. You need guys like Doug to make this stuff real, or make the science real, and then guys like me to turn this into a product.
Well, Doug, in what ways can material science drive more sustainable energy solutions? Could you give us some specific examples of the materials that could significantly reduce emissions?
Well, there are a lot of application areas, of course, to reduce emissions. I must say that in what we do and what we propose, the guardrails, if you will, towards that aim are not as strong as perhaps they should be. But on the other hand, we are encouraged to aim towards different material systems, like Alex is suggesting, that are materials that we can access more readily, that are less expensive, and still serve that same purpose. And Alex didn't say the words, but he's saying volumetric and gravimetric improvements. Electric vehicles, I believe, are about 15% more heavier. And so the tires wear out, the infrastructure of the highways will wear out, and so on. So we have to keep all of that in mind, and we be, well served to take and include that in all of our proposals when we submit them for energy storage, energy generation, things like that.
Is there anything that you're working on in your lab that you could cite as an example?
Well, yeah, it's for me, if everybody goes left, I go right in terms of popular materials. And I have been working on a capacitive energy approach that's not a battery, an electrochemical battery, but just something that will be able, like a carpet shock, in essence, a capacitor, be able to charge and discharge quite quickly and with high power. And that's really important for supply to meet demand. Unfortunately, it has a relatively high weight and volume, but on wind farms and solar farms, and perhaps the basement in your house, that's not such a big deal. So I've been working on materials like that. So can I twist and ask Alex a question? Sure. Alex, where do you find the balance between patents and trade secrets?
It's interesting, especially now, because you have this anti-China rhetoric, but the reality is the battery supply chain goes through China, and you have to learn to work with them and understand their motivations, and they really don't care about patents. They actually think it's you're holding society back by
Stifling creativity.
exactly. Now, when you work with your Chinese partners, you want to stay 1 or 2 steps ahead. And you do that by having trade secrets. One of the strategies we did in my last code, we actually filed dummy patents. Because if they knocked that off, you could actually see that they've been trying to copy your stuff. Pretty funny, because that it happens really fast. They iterate quickly. But patents are great. They give you a good head start, but materials are you can think of it a product by process. What that means is it's only as good as the process it's made. You don't patent the process. You know it's like baking a cake. Your cake, you might have all the ingredients, but you need the right temperature, the right times, etc. That's the process. You don't patent that. You can write it down and hide it or what have you, but that's one is to give you a head start, the other is to maintain your lead.
Okay, could I say your words differently? You can patent a process, but you can't enforce it.
So there's composition of matter patents, which actually gives you ownership of the material of the molecule, and then there's process patents, which how to make it. Those can be easily knocked off, but you don't tell your secret sauce to the U.S. government to get coverage. You just get the material and how to make it, etc. That's
So I also want to bring it back to wind technology. And James, what do advanced materials play in optimizing wind technology, and what advancements are you most excited about?
So before the panel, we talked a little bit about how batteries are in wind turbines. Actually getting renewables onto the grid on a system level, you've got to have a hybrid supply chain for that. But back to turbines, and I guess my area of expertise, which is blades, there's a huge amount of focus on material science. And it is a volume and a scale problem. I mean, for those that don't know, a blade is about 50 tons of material. It's exactly the length of probably a football field. So these are about 120 meters long, 50 tons of material, maybe 15 tons of carbon fiber, 15 tons of glass fiber, and then epoxy resin, which is obviously linked to oil and gas byproduct. You've got metals, you've got coppers, you've got lightning systems, Faraday cage, you've got condition monitoring systems, like scattering the innards of an iPhone. It's a really advanced structure, and you have to make that in 24 hours. So your mold line, which might have 100 people around it, is consuming material at such a high pace. That's usually where the problem with wind comes in. You can design an amazing structure like SpaceX does. It's the same materials that go into space that are going to Mars as you use to make a wind turbine blade. However, the cost structure is only enabled through throughput. So if you think of the burden cost of a material, you might be using a really advanced carbon fiber. And actually, those of you who know Professor Eric Smith from the Tulane Energy Institute, he's got a lot of expertise and focus, has a lot of novel ideas for advanced materials. He's got a background in oil and gas. There's a lot of conceptual ideas around how to manufacture carbon fiber here in the US to the sort of quality and volume that are needed to go into wind. So, and a blade is essentially like 2 aircraft wing skins with a large structural I-beam in the middle. And you have to get right down, if you're really into the base of the material science, it's about cross-linking polymers, so whether you choose thermoplastic or thermoset resins. There's a huge focus now on the full system. How green is the full system? So what's the end of life? Are you building in recyclable materials? These blades are working for 40 years. So when they're installed, the tip of the largest turbine in the world is not far off the height of the Empire State Building. So these are large units, and they're untouched for 40 years. So you have all sorts of hurricanes in our backyard. Okay, so you might have lightning strikes, you might have ice storms, you might have large pellets of water. How are you going to protect that product? How are you going to design it with fatigue in mind? And more importantly, how are you going to build in a supply chain that can keep up with the demand profile? So again, historically, the industry has to work with other countries, Japan, China, Europe, look at where other industries, almost like, a TRIZ, a sort of reverse engineering philosophy. What's automotive done? What's oil and gas done? What's aerospace done to get these supply chains up and running, and how to apply it to wind? And so it's really exciting on a system level. It's really interesting from a customer, what customers are wanting. Customers are the oil and gas companies, it's the utilities, it's customers that want to deploy 6,000, 7,000, 8,000 turbines a year, and they want it on a very specific price point because they're selling the power to us, to consumers. So you cannot use whatever material you want. And a lot of engineers that we work have, if they've come from another industry, they adjust in terms of this manufacturing-led design, this designing around a price point, very similar to battery tech. It can't be made of unobtainium, it can't be made too expensive. It's got to be really with the right combination of sciences, moving up the technology readiness spectrum like we talked about, to finally have these aggressive product launch cycles.
So you're based in Avondale. You have a prototype in Port Fourchon?
Correct. So we're a young company that are going to be a large blade supply company. Avondale used to employ 26,000 people. Your smallest wind energy plant probably employs 1,000 people. So when we chose where to put the company, you put it where big stuff has happened before. You can build ships, you can build parts of a wind turbine. We've got a lease area down at Port Fourchon. It's a technology turbine. It needs to be abused. It needs to run designed experiments. It needs to put advanced materials, technology. We want certain parts to fail at this tech site. So there's going to be a huge focus on material science, maybe battery backup, hybrid systems. We were just talking earlier that batteries have to be the right safety factor, the right price point, the right weight, the right size. All of these things on a system level are really fascinating, and we are at the cutting edge here in Louisiana.
That brings me to my next question. How can Louisiana's energy infrastructure integrate new materials to enhance renewable energy here in the state?
So first off, the reason I moved to Louisiana in 2010 was because of Dow Chemical. So we were a technology company back in the UK. We'd run out of space because the blades we were building and designing, there's not much real estate, on the coastline in the UK. We met Louisiana State, we met GNO, Cam is just here, and we got told about, hey, there's NASA, so you've got a base of composite expertise that's been applied to space testing. You've got Dow Chemical that are a huge part of the supply chain. They make the resin, and again, when you're talking about, so they were in a really important part. And then you've got this industrial horsepower that exists here. Just this state is not afraid of the energy business. Massive deployment of new technology, large systems, barging, monopiles, jackets, welding, material handling. The yard I'm on now, it can take. It's going to, in a year's time, it's going to be dealing with 90 rail cars can get on site, 150 trucks a day, 6 ships and a deep water port. All of that will be used to be able to turnkey manufacture from 2027 onwards. So it's just that's really the enticement.
What about magnetic materials for the generators?
Yeah, absolutely. American superconductor. There's a lot of technology companies on the generation side of things, whether it's a direct generator or a gearbox-driven standard. But it's not my personal area of expertise, so I'd butcher an explanation. But when I was at General Electric, it's a huge area of focus, getting more and more efficient generation.
Can I ask one more question? Wind power generation of hydrogen, electrolysis of hydrogen on site?
Yep. So there's a great program that's being run out of Louisiana, actually by GNO Inc., H to the Future. A lot of it's driven by economics. So there's a very specific price point. There's all sorts of different colors of hydrogen. There's a hydrogen pipeline, I think, from Texas to Florida. So we've got the infrastructure, and I think there's a lot of, from a turbine, it's almost if you curtail it, rather than turn the turbine off, you might as well use that power for something. I think that's how conceptually people are thinking about it. If you have to make profitable hydrogen from a wind turbine, it's the intermittency that causes an issue.
So I did want to ask a question about what role does digital technology or AI play in developing these advanced materials?
I'll take this one. Chime in after Doug. AI is a buzzword, but there actually is quite a bit of meat in it if you know how to use it. And just like you have engineering, and then you have subsets of engineering, you have AI, and then subsets of AI. So, using Group 1 as an example, our actual name is Group1.ai. And we leverage AI by using material informatics. This is basically advanced statistics and predictive modeling, predictive analytics to help you accelerate R&D and development and discovery. So I use batteries as an example. It's a tough field. You know, one of my favorite jokes is you have liars, you have damn liars, and you have battery scientists. You know, there's a new battery innovation every day. I get tired of reading journal publications because somebody's cracked the code of something and it's world changing. Doesn't make sense until you get it to scale. But regardless, there's about a rule of thumb. A new battery innovation takes $1 billion in 10 years to go from paper to something real. And the only way to accelerate that is to make better decisions, faster decisions. And I don't care if you have 1,000 PhDs on staff. Human plus machine will always be the smartest humans on the planet. So leveraging aspects of AI allows you to, let's say, go through 1,000 product iterations or experiments down to 20 or 10. And that's really the game. And knowing how to use these tools is actually the state of the art, and it will be the future. When I'm hiring, I find myself looking actually not for PhDs anymore, but for bachelors or MS who've got exposure to AI or not even coding ability. AI can code. You don't need to code, but learning these tools is one way to stay ahead. And when you're playing a game of catch up, like we're doing with climate change, because right now we're arguably behind where we want to be, this is one of the strongest tools we have at our disposal, and it's compounding, meaning it's growing faster than we actually are able to contemplate.
Anything that will stimulate progress in a faster way.
Absolutely.
Which does bring us back to our panel is about net zero. And I did want to ask the group, if we succeed in creating and implementing advanced materials at scale, like we're all talking about, what does that net zero world look like in 2050? I'll start with James.
So full cycle wind turbines, and again, you burn a lot of carbon to build the materials, to put the blades together, the turbines together, and you're offsetting carbon when you're generating. I think data, getting the right business case, getting the right data, getting the right source of truth. I really like this fail forward fast framework. So I think that it's a really applicable to wind energy as well. Being smarter at the way that products make it out there into industry. Smarter at the design experiment standpoint, not having waste, not having failure, not slowing things down. It is a race. I really like that. It is an aggressive competition, and the people that I meet love that. So I think by 2050, hopefully, there'll be a really efficient product and system integration machine. So wind energy is just part of the system. It's got its own problems with grid integration and transmission and intermittency. So I'd like to think that from wind, it's really well seamlessly integrated with batteries, solar, transmission, and I think that's being smart the way the collaboration occurs.
Doug, I see you wanting to jump in here.
Yeah, I'm sorry. Can I?
No, please.
So I think sometimes it's really important to work from the goal backwards, and that would involve policy changes that we just heard in the other room here, and I hope those policy changes happen. But no one yet has mentioned, in terms of materials, nuclear power. Now, I we can say, what materials have really changed. Well, hopefully it's our safety, small nuclear reactors that have been envisioned to just plug right into coal power plants because they have the turbines and the distribution and so on. And I think that's really important. I teach a class in energy, and when I ask my undergraduate students if they think nuclear is green, they all say yes. And, some say nuclear is carbon negative. So, I really think we have to include that. Okay. With respect to AI, I want to just mention that. I believe it was Google and Meta were sort of tampered down in terms of their nuclear ambitions, but they know how important nuclear power is because of how much energy AI is going to eat up. But lastly, I'd like to just say about, with respect to AI, what we put into the algorithms. I have a student working on machine learning and deconstructing the algorithms. Oftentimes what we put into machine learning and AI are preconceived notions that we generate, and we have to think outside the box. I have an email from 2 students today after being admonished by me from using ChatGPT too much and instead of their own creativity. So I really do believe in human creativity. However, we define that as a material. An algorithm, a material processing is critically important for developing new materials, and it's not going to come from preconceived notions on. We all thought the internet would make us smarter, and I think we'd agree that probably has not been the case. So as such, I'd rather step away from it and like to motivate and stimulate, in terms of material development, creative ideas from students. Okay, young people. I mean, you mentioned young people. Most people get their Nobel Prizes for work they did before they were 30, and it's because they don't know what they don't know. And
John Goodenough, who invented the battery, got it at 98.
All right, there you go. So I really I know it's benefit for improving the efficacy of processing materials once we've got something put together and optimizing, but I really do believe in the power of human creativity.
So Alex, what does that net zero world look like for you 25 years ahead?
I and this isn't just a plug. I genuinely believe there's a unique aspect that the Gulf Coast has in the type of engineers and type of thinking. I've spent time in Silicon Valley, in Austin, and those aren't engineers. Engineers, chemical engineers here, we know chemistry. We know molecules. And changing molecules and moving them and making them more cost effective we're born in, that's been in our DNA for decades. So once the old guard in oil and gas, which they are, that's how I used to fundraise. I would talk to guys in the oil and gas industry and say batteries are just little bags of chemicals. We all know chemicals. We can move them. They're BTUs and etc. But once you get past, and we are, you let me fast forward to answer your question directly. I keep having the obvious opportunity to me is we have generation, but also we need to store that energy and get the cheap electrons, and that's when we're talking load balancing and issues like that. Storing solar or storing whatever. I do believe fossil fuels will and need to remain in the picture, but we have to store that energy, and doing it from my perspective, that is the bottleneck in the energy transition, is how do we store these things. We could generate energy very cheaply, but getting it at the price point and the immediacy, that's why we're starting to look at, that's why people like natural gas, and that's why we're starting to look at nuclear, because it's such a gargantuan amount of energy that you can get on demand. But it's nuclear reactors take decades to go from broken ground to operating. So I really see a fertile opportunity here for marrying energy storage technologies, hopefully batteries, with energy generation technologies. And what we are masters here at is fossil fuels, but doing it smartly, I think, is the path forward. I have no doubt we can do that.
Thank you. I think we're at the point where questions from the audience, but I'm not sure if...
Yes, we do have a few questions.
Okay, great.
The first is the steel industry is a major contributor to global carbon emissions. Are there emerging material alternatives to steel for use in heavy industry, whether structural steel and or pipe?
I've got one answer on that with regards what I'm aware of in oil and gas that has applicability in renewables, and it's linked to composites, which is my specialist subject. So, steel can be replaced. Steel pipe, the miles and miles of steel pipe can be replaced with composite pipe, and no one really knows how far that can be taken, but it is. You've got to bond. Instead of welding, you bond, and that comes back to understanding molecules. What's your material science? What adhesives? How are you going to inspect it, with non-destructive testing? So there's a lot of applicability in fact, a lot of engineers that are in Gulf Wind technology started out in metals. And because you understand the fracture mechanics and the porosity and a lot of the molecular science, it can be applied to composites. So I think a lot of where applicable, composites has an ability to displace. The Dreamliner is a composite plane. It's got carbon fiber spars. It's got bonding technology. The service mechanism on that is done differently to traditional planes. So if you look at each industry, composites are in automobiles. If you make lighter automobiles, that's good, because when batteries maybe are heavier, but you can make lighter chassis. So you're going to see a lot more composites replacing metals or complementing it in the right way in the future.
Could I summarize it by saying, we have to look no pun intended, the global picture of each material. But there is no magic bullet, but I'd like to say there's a lot of helpful BBs, if you will.
Yeah.
And so, I found personally, and I've talked to many people, once you put a few solar panels on your roof, you have LED light bulbs. You start turning, up or down the thermostat. You add insulation. So it's sort of all of the above. But the construction industry, and especially cement, as you know, adds a lot to the carbon economy.
Are there any other questions?
Yes, we do. What impact will material extraction for batteries and renewable energy sources like wind turbines have on our environment in the next 5 to 10 years? And how can we be more sustainable in the future with extracting these materials?
I'll take this one, but I definitely hear your perspective. That's the ugly secret about batteries. Well, it's not a secret anymore. Critical minerals are incredibly important. You know, it's instead of emissions, we're arguably hiding the destructive nature of extracting and creating these materials by mining. And so there are several mandates now by industry to start looking at more sustainable methods of extraction. Now, for example, lithium extraction. You know, I know at least 50 companies looking at different ways to extract lithium, because typically, you know, rule of thumb, for every ton of lithium, you need 500,000 gallons of water. That's not sustainable, especially in a world that's getting hotter every day. So this is an issue that's not being swept under the rug anymore, but it arguably might be the most important issue in the energy transition. You know, you look at the need for all this electrification needs copper. More copper will be needed in the next 5 years than we've mined in the past 30. So there's a tremendous existential issue with sourcing minerals. So we need to look at avenues to extract, but also avenues to go without critical minerals.
Can I just add to that? You know, we're here talking about net zero, and the reason why is we have a better sense as humans for sort of the circular carbon economy cycle. But for these other minerals, it's my hope that we can take and reclaim and recycle them. I mean, we're not, you know, trying to sequester lithium out of the atmosphere. Yeah. So you know, it's my hope once we get it out, we can you know, use it again and use it often.
Yeah. I've got a thread I can follow there, and a lot of it comes down to the innovation problem statement you set engineers. So I know that my engineers, if they go to design a structure, you'll look at your characteristic values or material science that you've got, or bonding, structural material properties. And if you give a different problem statement, so if you want to remove balsa wood from a design, or if you want to remove epoxy resin, you want to move to a thermoplastic or a recycled material, you change the problem statement and you give it to a team of entrepreneurs, engineers. You give them a lab, a safe space, some funding, and you can design structures if you just remove the boundaries. If you make it easy and you give the characterization book, engineers, in my experience, will tend to use that data book. But if you create them in an innovation space, that's when you get the novel ideas and the application. Certainly in structural materials, linking to thermosets and some epoxy resins and structural cores, give an innovation problem statement.
Great.
We have time for one more question. Where are the raw materials for potassium ion batteries, and where does the supply chain run through?
Great question. So this is one of the value propositions of potassium batteries is that it involves no minerals sourced from areas of socioeconomic unrest. So no lithium from Chile or China, no cobalt from the Congo. The raw material is potash. That's 1,000 times more abundant than lithium, and it's widely distributed and is in abundance in North America. The remaining materials are what are used in existing battery supply chain. You've graphite anode, normal PPE or PPE separators, your electrolytes or normal organic solvents. You know, BASF has a plant in Zachary, and you know, Coro, they also make electrolyte salts, and they're in St. Gabriel. So the key is the raw material that go into potassium batteries is potash, KCl, KOH. You need K, which is potassium in a periodic table. No lithium, so no 500,000 gallons of water per ton. We're talking very, very abundant and humane critical mineral or mineral.
Well, I think that brings us to the end. Thank you, Alex. Thank you, Doug. And thank you, James, for sharing your insights with us today. I know I learned a lot. Thank you. And thank you for joining us here today.
All right, what's up?